Hello and welcome to Bachelor of Physics. You're going to have to bear with me today because I am a little congested. In any case, we're talking about electric fields and Coulombs Law and electric charge in general. Last time we left off talking about Charles Augustin de Coulomb, who realized that electric force is proportional to 1 over r squared. In other words, Coulomb's law is that the magnitude of the electric force between 2 point charges is directly proportional to the square of the distance between them. Mathematically, we would write that the magnitude of the force is equal to 1 over 4 pi epsilon naught, known as the electric constant, times the absolute value of Q naught, or the first charge, times Q1, or the second charge, over r squared, where r is the distance between the first charge and the second charge. Now, this entire first term here is known as the proportionality constant, or we denote it as K. The value of K is 8.99 times 10 to the 9th Newton meter squared over Coulomb squared. Now, the electric constant, the value for the electric constant, epsilon naught, is 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. And last time we talked about how the magnitude of the charge of the electron is equal to the magnitude of the charge of the proton. Well, that value is denoted as E, and it's known as 1.60 times 10 to the negative 19 coulombs. And there's two important things to note about Coulomb's law. Number one is that the principle of superposition still holds. In other words, if there's a force being exerted on a charge, the total force, the net force, is the sum of all the forces on that charge. So if we had not just a single charge exerting a force on this final charge, if we had 1, 2, 3, then the net charge on this last charge is going to be the sum of all the forces from all the charges. And the second thing is that Coulomb's law is for situations in a vacuum. You see, electric constant, or epsilon naught, is also known as the permittivity of free space, aka this proportionality constant works only for situations in a vacuum. If we're not in a vacuum, then we'd probably have to multiply by some constant that allows it to get to a closer value, say for situations in air or water or whatever. But say you have a situation where you have one charge on the left and one charge on the right. How does the charge on the right, if we're looking from the perspective of the charge on the left, how does the charge on the right know that the charge on the left is there and henceforth gets exerted a force on it? Well, one way to look at it is that when a charge is inserted in space, it modifies the properties of the space around it. And then when the second charge is put there, it senses the modified space, and its response is to be exerted F naught. Now, if we remove the second charge, Q naught, the space where that charge was would still, its properties would still be modified. And that's known as an electric field. In other words, it's force naught, or the force that Q exerts on Q naught, divided by Q naught. This is known, again, as electric force. And the electric force on a charged body is exerted by the electric field created by the other charged bodies. And we can actually get force from the electric field, right? So we know that the vector, by the way, it is a vector. The electric field has a direction. In this case, we denote it as r hat. But in any case, the vector E is equal to the vector F naught over Q naught. And so you can get F naught by multiplying Q naught by E. Mathematically, though, and properly, vector E, or the electric field, is equal to K, or 1 over 4 pi epsilon naught, times Q, which is the charge on the left, or the charge that we're looking from its perspective, over r squared times r hat. And again, r hat is basically a unit vector noting the direction of the electric field. Now, for positive points, the electric field always points in the same direction as r. Say, for example, here where r hat is pointing to the right, well, Since this is a positive point charge, the electric field is always going to point in the same direction as R. And it's the opposite for negative charges. If this was a negative charge, then the electric field being exerted would be the opposite direction as R. Of course, R is still the same direction, right? R hat is pointing to the right. If this was negative, then the electric field would be pointing to the left. In addition, E is not a single vector quantity, rather it is a vector field. In other words, there is an infinite set of vector quantities within a space. Sometimes this vector field is constant. For example, for a conductor, if there is an electric field within the conductor, that electric field is going to exert on force on all the different charges and give it net motion. However, since this is an electrostatic situation, it can't have net motion. And so by definition, we must conclude that in electrostatics, every point within a conductor has no electric field. Notice, I'm not talking about cavities within a conductor, I'm specifically talking about within that conductor. Now, while point charges are all well and good, most realistic situations are going to have some charge distribution. So let's take a rod, for example, or maybe a plate, or maybe even a sphere. We would have to calculate the sum of all the charges within the rod, or the plate, or the sphere, and then that force that the rod is exerting on the charge is going to be the sum of all the forces from the sum of all the charges. And so F naught in this case is equal to the sum of F from N to A, where A is however many charges there are in the rod, and the sum is of F sub N. However, since we're looking at a rod which is exerting a force on a single charge, there's going to be one charge that's the same for every term. And if we pull that out, we're actually going to get the sum of Q naught times E sub N, which brings us to the principle of superposition of electric fields, which states that if the electric field is equal to F naught over Q naught, then there is a sum from N to A of E sub N. Now for charge distributions, we typically deal with three different ones: linear charge density, surface charge density, and volume charge density. Linear charge density, which we denote as lambda, is charge over, let's say, a line, or meters, a single meters, not meters squared or meters cubed, just meters, over some distance. Surface charge density, or sigma, is charge over an area, for example, a plate, or maybe the surface area of a sphere or a circle. And volume charge density is rho, which is charge over meters cubed. Say the charge not only on a sphere, but within a sphere as well. Lastly, I'm going to talk about electric field lines. Now, we talked about how for positive point charges, the electric field is going to be in the same direction as R. And since the electric field is exerted in every direction, if we look at the electric field lines from a point charge, we'll see that they're just going in every direction. Now, say we place a positive charge on the left and a negative charge on the right. Well, the electric field lines would be skewed because they would sum together and would be different than it would be if there was just one charge. And it's also important to notice that the farther out the electric field line goes, the smaller the quantity that it would be. And now, when there are positive and negative charges, it looks different when it's two of the same charges. Since positive charges are attracted to negative charges and vice versa, positive charges repel each other. And so the electric field lines are also going to repel each other. And basically, these would be the imaginary electric field lines, or what an electric field would look like if we had it on paper. Obviously, we don't see the electric field out in space, at least with our bare eyes. Now, there is one more topic to talk about within this portion, and that is dipoles, but I think I'm going to make an example video for Coulombs Law first, and then I'll make a new concept video for dipoles. In any case, I hope to see you in the example video.